So the idea was, if you look at chemistry, electrochemistry in particular, it's very good at counting electrons. It's not very good at selectivity. And so the idea was, can you endow a surface with the selectivity properties of chemical reagents, but with the sensitivity of electrochemical measurements? And so the idea was to incorporate ligands on the surface, and there's an enormous literature on that. So you could choose specific ligands for specific elements, even in specific oxidation states, which is pretty amazing. So that was the force behind that. So I think analytical chemists borrow a lot from other subdisciplines. So the example I just mentioned was from inorganic chemistry. The same thing you can say about biochemistry. How do you immobilize an enzyme and retain its activity, which is the real trick? Then you generate a product that can be measured electrochemically. So in essence, in all of these approaches, the measurement step is always electrochemical, because that can be very sensitive and very quantitative. Whereas then the other approaches provide, let's say, the selectivity or the other components of the measurement itself. Fast forward a couple of decades, actually more like 3. And so the idea is, if you look at most electrochemical interfaces, they operate under conditions very far from equilibrium. And so the idea that you can look at before and after, that's really not very satisfactory. For instance, if you take a lithium-ion battery, right? And you've done some experiments and you want to see what's inside, so you open it up and then put it in a spectrometer, right? And my standard line, we've all written this line in some manuscript: the cell was opened and quickly transferred to a spectrometer, right? Unless that's like a microsecond, you're dead. Because you cannot assume that an interface that is so reactive is going to remain intact. And so we started, so the evolution goes to ex situ, which means nowhere near what's under operating conditions, in situ, which approximates that, but then operando really means that it's under the real operating conditions of the device. The experiments are a little bit more involved, but the interpretation is very direct because you're making no assumptions. And so we developed Operando X-ray methods, Operando transmission electron microscopy, mass spectrometry, confocal Raman. All of these things provide enormous information, both structurally, compositionally, and in terms of like vibrational spectroscopy for identification. And so the analytical chemistry of these things, let's say lithium-ion batteries, virtually all lithium-ion batteries operate beyond the thermodynamic limits of its components. So give it a reason and it'll go off. And so the trick is, how do you understand the chemical transformations, which is real analytical chemistry, on the time scales, which is kinetics, but coupled to that, so as to make sure that it ends when you want it, not when it wants. In a similar vein, let's say fuel cells and electrolyzers, again, the idea that you operate under conditions very far from equilibrium. And so one of the typical questions is, what does your catalyst look like? Not, outside the cell, inside the cell, under operating conditions, and the difference can be just dramatically different. The thing that really strikes me is how fortunate I've been with the people that have worked with me. I mean, my standard, answer to when people say, what are you most proud of? The people that have worked with me, both graduate students and postdocs, because that has a much more lasting value than anything else we do.
So the mentorship is
yes,
really important.
I've had 67 PhD students and about 80 postdocs, and that's a lot of people. At least from my perspective, that's a lot of people.